You ever look at a massive skyscraper or a huge bridge and just wonder, how is that thing not falling down? Well, it's not magic. It's this incredible, invisible science called statics, and it's basically the art of keeping things perfectly still. So let's dive into this hidden world that's literally holding our own world together.
At its heart, statics is really all about solving some pretty high-stakes balancing acts, and we're going to tackle one right now.
So, check this out. We've got a massive 40 kilonewton crate, that's more than 9,000 pounds by the way, just hanging there, suspended by 3 cables. So how can an engineer say with absolute certainty that those cables are going to hold? I mean, one wrong calculation, and this whole thing comes crashing down.
The answer is, it's not a guessing game. Not at all. Engineering is this really precise science, a process of identifying and measuring and balancing all these invisible forces that are pulling and pushing on an object. And to do that, well, engineers need a kind of special language.
This special language is what allows them to describe any force with perfect clarity. So let's take a look at the very first tool in our statics toolbox.
And the absolute core of that language is the concept of a vector. See, a vector isn't just a number. It's a number with a destination. It's got a magnitude, that's the how much part, and a direction, that's the which way part.
And this difference is super important. A scalar, like mass or volume, it just tells you how much. But a vector, like a force, it tells you both how much and which way. Think of it like this. It's the difference between saying a 50-pound weight and a 50-pound force pulling straight down. That direction, well, that changes everything.
Okay, so once we can describe the forces, how do we organize them all? How do we see the whole picture? For that, we need our second tool. We need a way to visualize the problem.
This right here is a non-negotiable rule in engineering. Seriously, before you write a single equation, you have to draw what's called a free body diagram, or an FBD. It's like the battle plan that shows every single force involved in the fight. And it's actually a pretty simple 3-step process. First, you isolate your object. Just get rid of all the background noise. Second, you draw arrows that represent every single force acting on it. And third, you label each of those forces so you know exactly what you're up against.
Let's see this in action right now. So we take this sphere, we isolate it from the wall and the ceiling, and what are we left with? Just 2 forces. Its weight pulling down and the tension in the cord, that's FCE, pulling up and away. Simple, clean, and suddenly you have everything you need to start solving. Okay, so we've got the language. That's vectors. We have the battle plan, the free body diagram. Now we just need the one law that governs the whole thing, the single most important principle for anything that's standing still. And here it is. Looks simple, right? Sigma F equals 0. This elegant little equation is the golden rule of statics. It just means that if you add up all the force vectors acting on an object, the result has to be 0. No net force. Zilch. Nada. Now, this might be ringing a bell from like high school physics class, and it should. It's Newton's first law. For an object to stay at rest, all the forces have to cancel each other out perfectly. It's literally the physics of standing still. So what this means in practice is actually really intuitive. Any force pulling up has to be canceled out by a force pulling down. Any push to the left has to be matched by a push to the right. When all of that happens, you get this state of perfect balance. Engineers have a word for it, equilibrium. Okay, we have our tools. We've got the language of vectors, we've got the free body diagram, and we've got the golden rule, sum of forces equals 0. Let's go back to our crate and solve this thing. First things first, we draw our battle plan. We isolate that single point where all 3 cables in the crate meet. Then, we draw an arrow straight down for the crate's weight, and 3 arrows pulling away for the tension in each cable. Next up, we use our secret language. We describe each of those cable forces as a vector. Now, we know their direction in 3D space, but we don't know their magnitude, their strength. That's the piece of the puzzle we need to find. And now, for the final step, we apply that golden rule. We say that the sum of all those force vectors has to equal 0. And this is what lets us build a set of equations where all the up, down, left, right, and forward, backward parts have to cancel each other out. And when we solve those equations, bam! We get our answer. The force, or the tension, in 2 of the main supporting cables is 23.6 kilonewtons each. So now the engineer can check that number against what the cable is rated for and know with mathematical certainty that it's safe. No guesswork involved. So you see, this isn't just about one crate. These exact same principles are being applied all around you every single day.
And this really matters.
Because this whole principle of equilibrium is what keeps our world standing. It's how engineers design bridges to handle the weight of traffic, and buildings to resist the force of the wind, and even airplanes to maintain steady flight. Statics is the absolute bedrock of safety.
So the next time you see a massive crane or you cross a bridge or, heck, even just sit down in a chair, take a second to remember that invisible balancing act. Everything is being held perfectly in place by forces canceling each other out in this silent, perfect equilibrium.
Which leads me to a final thought for you. As you're sitting there, the force of gravity is pulling you down, and the force of your chair is pushing you right back up. They're in perfect balance. So what other invisible forces are keeping you in equilibrium right this second?